Chapter 7. This is the first lesson for the next chapter, which is on rational expressions and equations. So the first thing that we need to do is we need to define what is a rational expression. So we go back to what are rational numbers. Rational numbers, simply put, it's a fraction. Definition-wise, they say it's a quotient of two integers. One integer divided by the other. Looks like a fraction. So in a rational expression, you have polynomials especially in your denominator. In order for it to be a rational expression, there has to be a variable in the denominator. So, for example, 7 over 2y plus 5, that is a rational expression. But if it was written the other way, 2y plus 5 over 7, that's not. This is just having everything divided by 7. In order for it to be considered a rational expression, the variable has to occur in the denominator. Sometimes you could have a binomial over a binomial. They could be the same degree. Sometimes they're not. So in these two examples, the degrees are not the same. This is a degree of 1 because the exponent is only 1. This would be a degree of 2. So a single variable rational expression is an algebraic fraction in one variable in which the numerator and the denominator are both polynomials. So what we will be doing in this chapter is we're going to add, subtract, multiply, and divide rational expressions, and then we're also going to look at solving rational equations. How do I add fractions? I need a common denominator. So if I have to add rational expressions, I'm going to need a common expression. How do you subtract fractions? Common denominator. So it's the same process. So for subtracting rational expressions, I need a common expression. So we will go through and investigate how do I get those common expressions. How do I make an expression that's common to these two? How do I multiply fractions?
You can multiply across.
Yeah, just straight across, simplify if I can. How do I divide fractions? Invert and multiply. So what we do for fractions, we do the exact same process for rational expressions. Only now we're dealing with algebra, we're dealing with expressions rather than just numbers. The key to operating with these rational expressions goes back to factoring. So chapter 4 and chapter 5 to a certain extent play into this chapter. So if you recall the methods for factoring polynomials, the first method we always look for is, can I pull out a common factor from each term? Then we look for a difference of squares. So if I have a binomial, I look to see if it's a difference of squares. If I have a trinomial, we have the three ways. We can do inspection, decomposition, or we can do that sight method when I have something like a 2x squared. And then grouping. Grouping is when I have 4 terms. So, and grouping connects itself to decomposition. Because in decomposition, what I would do is if I had 2x squared plus 8x not a good example because I could divide everything by 2. But if I had something like this, I could rewrite my polynomial with 4 terms. That's decomposition. So I take the 8x and I write it as a 2x and a 6x. The reason why I would choose 2 and 6 is because that answers the question of 2 numbers that add to 8 and multiply to 12. And then I factor by grouping those 2 sets. That's decomposition. And then grouping would be if I started off with this. If I started off with 4 terms, can I group them into groups of 2 and find common factors? So it says, consider the rational expression 2x plus 2 over x squared plus 3x plus 2 and 2 over x plus 2. And we're asked to complete the table. So I'm going to show you a trick that you can do for this, because Really what I'm concerned with is seeing if there's a pattern between these. Not going through and seeing whether or not you can actually go 2 times 0 plus 2 divided by all of that. So what we do is we grab our calculator and we go into our y equals and we let y1 be equal to 2x plus 2. So I have to put that in brackets. 2x plus 2 divided by, and then I put the bottom in brackets. It's important to put brackets around the top expression and the bottom expression because this division bar implies that I do this operation first, and then I do this operation, and then I divide the two results. So I have to keep order of operations clear. Once I've entered that in, I'm going to go to my table. So second table. And I get these values in here that correspond to 0, 1, 2, 3, and 4. So if I look at 0, what is the value of that expression at 0? 1. What is the value of the expression at 1? 2/3. Thank you. So take the decimal and convert it into a fraction. What about when x equals 2? 1/2. When x equals 3? 2/5. And when x equals 4? 1/3. So now if I do the same process for the 2 divided by x plus 2. So clear off what you have in y1 and start over. 2 divided by bracket x plus 2. And then go to my table, and what do you notice? They're the same values. So we're going to copy this chart in again. So if the values are the same for each of my inputs, what does that tell you about the two expressions? So they have to be equal to each other. So what can we say about the values of the rational expressions when x is replaced? They're equal. Which means that these two forms have to be equivalent to each other. So in terms of fractions, these two rational expressions would be the same as saying 1/2 is equal to 2/4. One of these expressions would be kind of my 1/2 and the other one would be my 2/4. So if I look at the 2x plus 2 and the x squared plus 3x plus 2. If I look at 2x plus 2, I can factor out a 2. 2 is common for each of those. Now if I factor a 2 out, I'm left with an x plus 1. If I look at the denominator, x squared plus 3x plus 2, it's a trinomial. I can factor this by inspection. Two numbers that multiply to 2 and add to 3. 2 and 1. So what would my two binomials then be?
X plus 2, x plus 1.
Now, next question. What's 4 divided by 4? 8 divided by 8. Negative 20 divided by negative 20. Anything divided by itself? 1. So if I have x plus 1 and I'm dividing it by x plus 1, what would that equal? 1. These, in sense, would cancel out, which would leave me with 2 for the numerator and x plus 2 for the denominator. This is my 1/2. This would be my 2/4. So the 2 over x plus 2 becomes my simplified form. So the procedure that we used is we factored the numerator and the denominator wherever possible, and then we canceled common factors. Not numbers, we have to cancel the common factor. Okay, so I can't cancel this 2 with this 2, because this 2 down here is tied with the x. This is not just 2, it's x plus 2. Okay? So right here again, to reduce fractions, we cancel out factors, not terms. Okay, so we have the same 2 questions again, or the same 2 expressions again. We already have the 2 over x plus 2 in our calculator, so we're going to pull that up again. Only this time we're looking at the negatives, so I go up in my chart. So when x equals 0, the value of 2 over x plus 2 is 1. When x equals -1, the value is, when x equals -2, the value is, it's an error. So we'll just leave that blank for now. And when x equals -3, the value is -2. So I have 1, so 1, 2, and negative, 1, 2, and -2. So let's take a look at this when x equals -2, and we'll actually physically input this in. I have 2 on the top, and then on the bottom I substitute in a -2. And what is -2 plus 2? 0. And what happens if I try to go 2 divided by 0? You can't divide by 0, so we call this undefined. Yeah, we say it's undefined. So now we're going to do the same thing for the 2x plus 2 over x squared plus 3x plus 2. So I actually want you, even though we know that the 2 reduce down to the same expression, I want you to input the entire expression in and check those 3 values again. So if I look at my table of values this time, what do I notice? Are they the exact same value each time? No, I have the 1 and the -2 stayed the same. This comes up as an error, and this comes up as an error. So we're going to do the math behind these two to see what they look like. So I've got 1 and -2. So for this one, 2 times -2 plus 2, or sorry, 2 times -1 plus 2. What's 2 times -1?
-2.
And -2 plus 2 is? Okay, so the top would equal 0. And then the bottom, I would get -1 squared, which is 1, plus 3 times -1, which would be -3, so 1 plus -3. And -2 plus 2? 0. Now, this one's a little bit of, it's not a trick one, but instead of saying that it's undefined, what we say is it's indeterminate. And it only happens when I have 0 over 0. Because what did I just tell you? Something divided by itself always equals 1. This is the exception. 0 divided by 0 does not equal 1. It's indeterminate. So now if I look at the -2, 2 times -2 is -4. -4 plus 2 is negative 2. And then for the bottom, I have negative 2 squared, which would be 4 plus 3 times negative 2, which is negative 6. So I now have 4 plus negative 6 is negative 2, plus 2 is 0. So there's my undefined. So when we look at this, it says for which expressions, or for which values of x, is this first expression not defined? At negative 1 and 2. Whereas 2 over x plus 2 is undefined only when x equals negative 2. Why are these expressions not defined? Why did these become undefined expressions? The denominators were 0. So denominator equals 0, and I cannot divide by 0. Now, the values of the variable which result in the value of this rational expression not being defined, so for example, the negative 1 and the negative 2, are considered to be non-permissible value. So non-permissible meaning you don't have permission. So negative 1 and negative 2 are non-permissible values for this expression. They could also be considered restrictions of the expression. I can put any other value of x into here and it'll work out, but I cannot put negative 1 or negative 2. In this expression, my non-permissible value would be x can equal negative 2. That would be my restriction. So non-permissible values, this is important, are values of the variable that make the denominator equal to 0. So instead of having to come up with a table of values and guessing and checking and trying to pull numbers out of the air to find out what my non-permissible values are, I can look directly at the denominator, let the denominator equal 0, and solve for it. So if I look at that 2 over x plus 2, if I let this denominator equal 0, the value of x would then equal negative 2. When I take x squared plus 3x plus 2 and let it equal 0, we're now back to chapter 4, chapter 5, when we were solving quadratics. When we have a trinomial, what's the first thing that we try to do? Okay, I don't have a greatest common factor, so then I would factor by inspection, and what do I get? X plus 2, x plus 1. And then that 0 property law, or that 0 law that we did at the beginning of chapter 4, says if either one of these factors is 0, the whole thing would equal 0. So when does x plus 2 equal 0? And when does x plus 1 equal 0? When x equals negative 1. So to answer the question as to why they have different restrictions, it's because before I simplify this expression to that form, this is what my denominator equaled. So when I put negative 2 into this expression, it equaled 0, or into the denominator. But when I put negative 1 in here, it also equaled 0. So when I'm looking at my restrictions, at my non-permissible values, I have to look at the original expression. Not the simplified, the original. So you have to go back to what that original expression was. And non-permissible values are present every time we have a denominator, an expression in the denominator. So if you have a variable in the denominator's position, chances are very, very high you would have a non-permissible. Okay? There is, I should say each time, because if I had this, I wouldn't actually have a non-permissible value, because every time I take an x and I square it, I'm going to get a positive number. I'll never get a -4. So this would be kind of an exception to the rule. But 90% of the time, you're going to have a restriction there. Rational expressions are considered to be simplified if they have no common factors, the same way as fractions are simplified when they have no common factors. So if we look at class example number 1, we are stating non-permissible values and we are expressing these in simplest form. So when you are stating the non-permissible values, start off with your original equation. So start off with the original denominator. If I look at 2x, let it equal 0. Or in this case, it's not that I let it equal 0, it's that it can't equal 0. So if 2x can't equal 0, how do I get rid of the 2? How would I get x by itself? And when I divide it by 2, what do I get? 0 divided by 2 is 0. So x can't equal 0. So now if I go to simplify this, 12 divided by 2, 6. And x squared divided by x, x. So in this expression of 6x, x could actually be equal to 0, but we have to put the restriction here because it goes back to the original question. In the original question, x couldn't equal 0. Does that make sense? So if I look at b, I've got factors on the bottom, so I look at what the restrictions are on each factor. If a plus 7 can't equal 0, what can't a equal? -7. And if a plus 1 can't equal 0, a can't equal -1. So those are my restrictions. Now I look at simplifying. Do the numerator and the denominator have any common factors? A plus 1. So it's going to cancel the top and the bottom. So I'm left with a minus 6 and a plus 7. What do you notice about question C? It's in general form. So I have this non-factored trinomial. So start off with factoring it. It'll be far easier to find out my restrictions when it's in this type of a form than when it's in this type of form. So can you factor by inspection? Two numbers that multiply to -20 and add to -1. Okay? So -5 and 4 would be y minus 5 and y plus 4. So now I look at my two factors in the denominator and I let each of those be equal to 0 to find my restrictions. So what couldn't y equal with my denominators? 5 and -4. And then when I go to simplify this, what are my common factors that can cancel out? So if I cancel the y plus 4s, what does that leave me with for the numerator? It's 1. Because y plus 4 divided by y plus 4 is going to equal 1. So I get 1 over y minus 5. Okay, so now if I look at the last one, if I go to, this time I have to factor both the top and the bottom because that's going to help me simplify. So if I go to factor the top, two numbers that multiply to 28 and add to 11. 7 and 4. So y plus 7, y plus 4. What do I have on the bottom? Not a perfect square. Difference of squares. So how would I factor that difference of squares?
Just square root it.
So what would I get?
X plus 7, x minus 7.
Mm-hmm. Oh, why do I have y's here? I should have x's, shouldn't I? X plus 7, x plus 4, x plus 7, x minus 7. So what are my non-permissible values? What can't x equal? Right? And then what factor cancels out? The x plus 7s. Leaving me with x plus 4 over x minus 7. And again, this negative 7, it fits in this equation because I get negative 14 on the bottom. But it doesn't fit in the top equation. And that's where I always have to go up to. I always have to look at my original. So your questions. Three, B, and D. Five, A, C, E, and G. 6, 7,